Hello and welcome to this tutorial on ordinary least squares algorithm by Analytics School Online. I hope you enjoy and learn this fundamental concept and enhance your analytical skills to create regression models in the future. So let's see, what do we have? So on a bright summer morning, your friend Joey calls you up and he sounds really worried. He says he wants your help to guess the exact number of mango cartons to buy for his father's fruit shop, and so he can help his father make sufficient profits and also prevent potential losses occurring from the rotten mangoes in his inventory. And so, Superman to the rescue. Well, being a good friend, you decide to use your analytical skills and your skills as a data analyst to help your friend. But wait, what would you need? You ask him for his past year sales record and obviously a promise of a pizza treat. Let's face it guys, we all like pizza. So you get back to work and you try to search for an algorithm which can solve your problem, and then you come across OLS. The OLS method, the ordinary least squares method, and how you can use regression to predict the future is what you are interested in. And also you're going to learn something incredible to anchor to your memory and worth adding to your analytical toolkit. Let's begin with what? What is OLS? Basically, it's a statistical technique composed of algebra and statistics which helps us estimate the unknown parameters of a model. And this model, or as we say, the regression model, is capable of predicting future values based on past values. This algorithm basically defines the strength of correlation, or fundamentally the strength of relationship between two variables or quantities. And yes, if you're wondering right now, more milk does get more Oreos. Well, that's how I drank my milk. Let's now understand the real life significance of this algorithm. Like practically, why? What is it worth the effort? Well, let me tell you, OLS is used almost everywhere wherever there is a need of prediction. It is applied on economic datasets to describe economic systems. Data analysis in various fields like business, finance, and commerce use data analytics, where OLS is one of the most primary algorithms implemented. It also finds its use in marketing and sales strategy formations. So let's get started. Now, what are the prerequisites to apply OLS? Easy peasy. The data that we apply it on must be linear, and that's it. That's the only condition you require to apply the OLS method. We'll go through the concept of linearity in the coming slides, and till now we just get to know and keep it to our memory that whenever we start analyzing any form of data, we first need to visualize this data by plotting them on a graph and getting to know if it's linear. If it's not linear, it's not worth it, but if it is, you can proceed, and that's what we are going to do. Let me explain the concept of linearity. Linearity is a property that basically defines the relationship between two quantities. For example, we can see there are 5 lines in this diagram. The line A, which has a negative slope, the line C, which has 0 slope, the line B, which has a positive slope, and D and E, who have varying slopes. So what we must understand from linearity is that the line or the plot that we are visualizing must have a constant slope, or at least a roughly constant slope. There are going to be variations in the data set, but if you can observe a slight straight line inside the data set, you can be pretty sure that it's linear. For example, you can plot the graph between study hours and results. So the more you study, the better results you get. It's a simple concept, and in our learning, we must always define linearity of a straight line with the equation y equals ax plus b, where a and b are constant, x is one variable plotted on the x-axis, and y is another variable plotted on the y-axis. Now, so first we need to understand whether we can actually apply this to our problem, and that is slightly checking to remind ourselves of our ultimate goal, to help Joey. So we first observe linearity, and yes, we can see that there is a great linearity in the model in our data set, And so we can now create our predictor and move ahead with OLS. And oh, I can already imagine Joey's happy face when I help him, and I can just feel it. He's going to be so happy. Let's understand this. In OLS, when we try to estimate our predictors, we must first understand it on a larger level. Now, here is a simple data set of the Amazon stock price, and we are going to try to predict the prices of the Amazon stock based on the past values that we already have. So we first need to understand our data set. Our data set consists of two columns, the open price column of the Amazon stock and the close price column of the Amazon stock. Now, observing the data set, we can see that these are various numbers. For example, this is a $1,616 open price of Amazon stock for the month of July 2018, and the close price happens to be slightly lower, to be $1,588. And similarly, we can see that there is a decrease in the price for around 1, 2, 3, 4 and 5 days. But what do you observe on the 6th day? There is a magnificent increase in the price of the Amazon stock. Then again there is a decrease, increase, decrease, and so it goes on. So looking at the data, you cannot just understand if it's linear or not. So what do? We create a scatter plot of the open and close prices, and we analyze linearity. We've kept open price for the Amazon stock on the x-axis and close price of the Amazon stock on the y-axis, and plotting our data points, we can efficiently see that it is a linear data set. Like the close price of Amazon is moving relatively in a particular fashion with respect to the open price of Amazon stock. So we've done our first step. We've observed linearity. What next? Next is we understand the basics of the model. Now these blue points right over here are our observed data points, the data points that are already present and we know about them. We are not going to predict them, we are just going to use them to predict further. And these three lines, as you can see, the orange line, the pink line and the green line, are the various regression models that we can create for this data sets. These can divide the data points in various ways, and that, my friends, the line will help us predict future values. Before getting started with the OLS algorithm, let me explain to you what we mean by independent variable and dependent variable. We've plotted the x-axis with our independent variable, as we call the open price, and we've plotted the y-axis with dependent variable y. Now the basic difference between independent and dependent variables is that independent variable is not constrained under anything. It has its own personal understanding and it moves in a particular way, the way we define it. But our dependent variable y is constrained with our variable x. It can only move in a certain way, the way which x moves. So if x moves higher, y is supposed to move higher, as we are already considering linear data sets. And that, my friends, is the difference between dependent and independent variables. Now let's try to understand the least squares concept in general. In the least squares concept, we are trying to calculate the difference between the observed data points yi and the predicted regression line points for the same x, y cap. Our goal is to minimize the squared sum of these differences, and that, my friends, is going to derive our model's parameters. Now what is the regression model? It's simply a line equation, and a line, as I told you, is defined by y equals mx plus b. Now x and y are our independent and dependent variables, and a and b are constants. So our goal is to find those constants. Sometimes, let me just give you a little extra information, sometimes these differences are also called residuals, as they are the differences between the residuals from yi and yi cap. Analyzing and looking at it visually, we can see that this is our original data point or our observed data point yi. And let's assume that this is our regression model. This is our regression line which we are going to use to predict values. Now the line where it passes from the data point perpendicular to the x-axis, this point is called the predicted yi cap. So this is our observed point and this is our predicted point for the data set. And the difference between these two, as we can see here, distance between this observed data point and this predicted data point, D1, D2, and so on till Dn, as many number of points we have. So what is our aim? Our goal is to minimize this sum of squares, D1 square, D2 square, D3 square till n. And if we minimize this sum, we finally get the results in which we have the parameters for our line, our regression model. Now let me tell you something about the significance of this squares. When you look at this data set, when you try to visualize it, you are going to see that sometimes the predicted values are smaller than the observed values, and sometimes the predicted values are higher up on the y-axis than the observed values. So if you simply try to calculate D1 or D2, you might get positive and negative values altogether. But our goal is to analyze the relationship between them, and we cannot let the positives and negatives to cancel each other out and spoil our relationship or correlationship between the data sets. So we generally square them and then try to analyze their relationship. So our regression model is basically a line equation as I just said. So let us define our line equation. Let the line be called y equals b0 plus b1x, where b0 is our intercept parameter for the line, the point where the line crosses the y-axis, and b1 is our slope parameter, the angle at which the line is inclined with the x-axis. I can simply tell you the formula about the slope parameters. And as you can see on your screens, b1 equals the sum of the product of xi, where xi is our observed data point and xm is our mean. Mean, let me tell you, is the calculation as you can see below. Mean is the sum of the total x divided by n. So the sum of x is the sum of the data of x. For example, if x values is 1, 3 and 5, the sum of x would be 1 plus 3 plus 5, and since we have 3 data points 1, 3 and 5, the value of n would be 3. So our mean would be calculated by adding all the values of x dividing by the total number of observations in x, and similarly for y mean also. So our slope parameter is given by the formula of summation of the product of xi minus xm and yi minus ym, summing it over all data points, dividing it by the summation of xi minus xm squared. Xi minus xm squared is for all the data points with the difference between the observed data point and the mean value of the data points. So we've got the formula for slope parameter. Now we come to intercept parameter. Now as we already observed in our line equation, y equals b0 plus b1x, if we get to know the value of b1, it is very simple to understand the value of b0, as we can simply put this algebraic factor on the left side and simply subtract b1x from y and observe the parameter value of b0, and that's what we do. b0 equals ym minus b1xm. Now you may ask why I replaced y with ym and x with xm. Well, average is one of the most used methods to basically calculate the real value or a single value for all the observed points. So we replace y with ym and x with xm. b1 is given by this equation as we've already encountered, and b0 is the value by solving this equation. So as you can visualize b0 is the point where our regression model, our line, intersects with the y-axis. Now this can be in the negative y-axis, this can also pass through the origin, or this might also pass through the x-axis, where our intercept parameter would eventually cross the negative y-axis and give our intercept parameter. So moving on, after getting the slope and the intercept parameters from the equation, we are done. We finally plot the line from the line equation that we've observed. Looking at this data set which we encountered earlier, this red line gives our linear regression model which we've encountered or acquired from our OLS algorithm. Now how do you predict future values or even predict values that you could not observe from this model? Now for a x value or the independent variable x, a value or a data point in x can be simply projected perpendicular to the x-axis, and we observe the point where it intersects with our linear regression model or our line. Now from this point of intersection we again project a line, this time parallel to the x-axis and perpendicular to the y-axis, and the intersection or the point of intersection of this line with the y-axis gives us our y value or our dependent value prediction. And so we finally have our prediction for a value which we could not observe in our data set. To give you a short example, let's create our own small model. We'll go through this quickly because there are a lot of calculations which can be simply computed from the computers, and we have various algorithms and libraries to solve these problems. So let's get started. We have a variable x. Let me remind you, this variable x is our independent variable. It is simply a random data, a collection of random numbers. Well, you can see a little relation between them as they differ by 2, but do not get confused with it. These are simple data points which are independent. We've taken a set of 10 data points, and with respect to the variable x, we have various values of y which are again dependent variables on x, but are randomly separated. We are going to encounter their relationship once we visualize, but presently we have these data sets in mind. So moving on further, we first start to visualize, as we know that linearity is the only condition to use our model, our OLS algorithm. So we plot this, we plot a scatter plot on these two variables, x, the value x of our independent variable, and the values y of our dependent variable, and we observe a great deal of linearity between these 2 points x and y. Moving ahead, we try to first calculate the mean values of x. So here you can see we sum all the values of x, and then the total number of observations is 10. So we simply divide the sum of values of x by the total number of observations, and here it is. This is our x mean value, or the mean of x. Similarly, we calculate the mean of y. We sum the values of y and we obtain a value, and then we divide it by the total number of observations of y, and we obtain the value of mean of y. Now last set of calculations is the slope calculation. Putting the values of x and y in the formula as given here, we can simply put the values of xi and the x mean, yi and the y mean, and similarly for different values of x and y, we simply subtract the mean values 10 and 47 as we calculated in the last slide, and divide it by the values of the square sums of xi minus x mean. You can see here 1, 3, 5, 7, 9 till 17 and 19 subtracted from 10, the mean value of x, and all squared and summed together. So from these calculations we finally get the value of b1, 1334 divided by 330, and that gives us the value of our slope parameter, which comes out to be 4.0424. So we've already placed these values for the slope parameter. Now we use the slope parameter to calculate the intercept parameter, and as given by our equation, we simply put the y mean 47, the b1 value of 4.0424, and the x mean value of 10, and we acquire a value of b naught to be 6.576. So our equation of our line of our regression model is finally y equals 6.576 plus 4.0424 into x. We use it to plot a line on our data set, and here it is. Phew, that was superbly amazing, and we guys did it really well. We could plot this line very quickly and very efficiently, and we can see that now we have a predictor. Some of the data points are really well predicted already. They fall very close to the line, almost all the line, and the differences between the observed data points and the predicted values are very less, and so we've already created a very good model for our data set. Now coming back to the problem, we finally get to work with Joe's data set, and we perform the calculations as we've already done and derive the final model. And that's my boy. That is the linear regression model that we've come across, and now we'll use it to predict the number of mango cartons and help Joe out. So from the month of June, where his father needs the number of cartons that he wants to buy, we project a straight line perpendicular to the x-axis, and from the point of intersection of this line with our model, we again project a straight line parallel to the x-axis, and the point of intersection of this line with our y-axis gives us our final prediction, and that comes out to be 420. So you go up to Joey's place and you tell him that he's going to need 420 cartons. He seems surprised and he asks why, and you simply say it's magic. You used your skills as a data analyst and you came across a value which is going to be the best shot for Joey to buy the number of mango cartons, which is equal to 420. And finally the day comes, the month of July, where Joey comes home and tells you that you were right. He needed exactly 420 cartons and he could help his father to obtain sufficient profits from his fruit shop. And as promised, you both order a pizza and enjoy a pizza as best friends. Now let me tell you that with great power of this algorithm, we also have great responsibilities which we must follow to efficiently use this algorithm. Now, as we've already come across, OLS is a highly effective algorithm to predict values and has been used for a long time to model data sets and understand the strength of their relationships. It can be used for multiple variables as well. Like in our examples, we've only considered one independent variable x. We might use this over several other variables like x1, x2, x3 and so on, and we can still predict models for the dependent variable y. As you've already seen, we could simply examine a problem and solve it so quickly that we understood that it's very easy computation. So it is going to be easier for your processor of your computer, and it can be quick and efficient also. Now, with these pros, with these advantages, there are some disadvantages too. Now, OLS, or ordinary least squares regression, is strictly valid for linear relations only, and they do not perform well. In fact, they do not perform at all under non-linear relations like polynomial relations, support vectors, or decision tree concepts in classifications, which we are going to learn later. And most models in real life are non-linear. In some models, we generally try to predict values which are linear and then use those values to predict non-linear values in further or advanced stages of analyzing that data set, and thus it is very constrained with its applications to only linear data sets. And finally, it was a good day for all of us. We all learned something very interesting, and that's the end. See you soon in the next tutorial. Thank you.